Hello everyone, so this is the GCSE Combined Science Trilogy Physics Paper 2 walkthrough, and this is the foundation tier paper that pupils sat in June 2019. I'm going to go through and model how I would have tackled it question by question. I've attached in the description a link to the blank copy of the paper and a mark scheme, and I've put revision videos question by question if you need to go back and revise the content for that. Okay, so starting off with then, number one, magnetic force is a non-contact force. Which of these are also non-contact forces? So a non-contact force is when you've got a force acting on an object, but it's not touching. So we can use that to think about these different options. Well, air resistance, as you are falling down, if an object is falling down through the air, it will still be colliding with the air. So air resistance is a contact force, so it's not that. Electrostatic, so that's when you've got positive and negative charges, a bit like when you've got your hair standing on end after you rub it with a balloon. So if you've got the hair standing on end and you bring a charged balloon by it, okay, it would get attraction over a distance, and you don't actually have to touch the hair to move it, so electrostatic would be a non-contact. Friction is when you rub things together, so that would be a contact. Gravitational. Now gravitational is obviously just gravity. Now gravity, when we're on the earth, there's nothing physically touching us, pulling us down to the earth, so we describe it as a non-contact force. And the last one, tension, where if you put tension into like a rope, then you've got to twist it. And obviously that would require touching it to do it. So that would be a contact force. So it's electrostatic and gravitational are your non-contact forces. Question 1.2. Figure 1 shows a bar magnet and you've got 4 positions A, B, C and D. Which letter shows the position where the magnetic field around the bar magnet is strongest? Well, we should remember that on a bar magnet, the magnetic field lines come out of the North Pole and they go round to the south. Okay. Now, the field lines are strongest when they are closest together, and that tends to happen at the poles. So, B is further away than D though. D is right by a pole, so we would expect D to be where the magnetic field is strongest. Question 1.3. When 2 bar magnets are brought close together, they can exert a force on each other. Describe how 2 bar magnets can be used to demonstrate a force of attraction and a force of repulsion. So this is quite a complex way of saying what happens, or what you have to do to get magnets to attract, and what do you have to get them to repel. So to make magnets attract, that is what happens when you bring a north pole and a south pole together, or opposite poles. So force of attraction, you would say opposite poles brought together attract. Now the force of repulsion, that happens when you get 2 like poles or 2 similar poles. Happens when 2 similar poles are brought together, e.g. north and north and south and south. So figure 2 shows some paper clips that are attracted to a permanent magnet. You've got the south pole and the north pole. The paper clips become magnetized when they are close to the permanent magnet. What's the name of this type of magnetism? So when you've got a magnetic material like these iron paper clips and they're brought into the magnetic field of a permanent magnet, they can become magnetized themselves, okay, and they make their own temporary little magnets, okay, and we call this type of magnetism induced magnetism, because if you take the paper clips away, they would then lose their magnetism. So it's not forced magnetism and it's not strong magnetism. It then says label the north pole and the south pole of the 2 magnetized paper clips on figure 2. Well, we've just said that opposite poles attract. So if these 2 magnets become a temporary magnet, it would become south, would be attracted to the north pole of that induced paper clip. then the other pole would be a south, then you'd have the north pole again attracting to the south, and the south pole being at the bottom. So NS, NS on your paper clips. Question 2 then. Figure 3 shows a gymnast on a piece of gymnastic equipment. The equipment consists of 2 bars at different heights. The gymnast exerts a downward force on the bar. What is the size of the upward force acting against the gymnast on the bar? So we can see that this gymnast is just stationary, hanging from a bar. She's got a certain amount of weight pulling her down. Now, if she's stationary, that means that the forces would be balanced, okay? Because she's not falling down, she's not moving up, so therefore forces are balanced. So out of the options, it's greater than the downward force. No, wouldn't be that. It is less than the downward force. Wouldn't be that. It is the same size. Yeah, because if she's not moving, forces are balanced. Then question 2.2. Why is the weight of the gymnast represented by an arrow? Okay. Now the arrows on representing forces are giving a direction. And we should remember the difference between a scalar and a vector. A scalar is a quantity that just has magnitude or an amount or a value, like speed or time or mass. Whereas a vector is a quantity that has a size, like a magnitude, and a direction attached to it. Okay, so forces are vectors, okay, because they work in a certain direction. Weight is constant then, from out of these options, weight is constant. Well, that's not why we have an arrow with a direction attached to it. It's not a scalar. It's not just because it's a unit. It's because weight is a vector, because it has a direction. Question 2.3. Figure 3 shows the weight of a gymnast acting from a point. What is the name given to this point? Well, if we look at this point on the diagram, it's coming from the centre of the gymnast, okay, and we call that point, it's not her centre of force, it's not her centre of tension, it's not her centre of weight, it's her centre of mass. The central point of an object's mass we call the centre of mass. Question 2.4 then. The gymnast has a mass of 45 kilograms. The gravitational field strength on Earth is 9.8 Newton kilograms. Calculate the weight of the gymnast and it gives us the equation weight equals mass times gravity. Now they've given us the equation and there's no tricks with the units. It's in kilograms and Newton kilograms. So it's just an easy times together calculation. Weight is our unknown, our mass is 45, our gravity is 9.8. So 45 times by 9.8 is 441. And it's given us the units as well, newtons. Because force is weight is a force, and we measure forces in newtons. Question 2.5 then. The gymnast swings from one bar to the other several times. Describe how the gravitational potential energy store and the kinetic energy store of the gymnast changes as she moves between the bars. So just remember, she's got 2 bars at different heights, one higher up and then one lower down, and she's swinging from one to the other. So what this question is asking then is how the gravitational potential energy store and the kinetic store changes as she moves down. Well, let's start off with her on the high bar. When she's on the high bar, as she is higher, she has more gravitational potential energy. Okay? Now, as she moves down to the lower bar, she will lose GPE energy, okay? And that energy will then be converted into kinetic energy because she is using that gravitational potential energy to have more speed. So as she jumps or moves to the lower bar, the GPE is converted to kinetic energy. And question 2.6 then. Falling on a crash mat reduces the average deceleration of a gymnast compared with falling on a hard surface. Explain why reducing the deceleration is important to the gymnast. Well, if you're reducing the deceleration, you're going to be reducing the force. If you fall on a really hard surface, as you collide, all of that force is going to hit you at one specific time. But if you land on something that is quite soft, like a crash mat, the collision will go over a much longer period of time. So therefore that force gets spread out. So you would say the force of a crash mat reduces the force on the gymnast. So therefore there's less chance of injury. It's the same principle that children's playgrounds also have. They have that spongy, foamy material around the swings, because if a child falls off, if they're not hitting a very hard surface, they're hitting a softer surface, which will increase the time of the collision and therefore reduce the force on the child. So if they put it in that situation, it's the same principle. Question 3 then. Figure 4 shows two children playing table tennis. The boy hits the ball from one end of the table. Why does the velocity of the ball change when the boy hits it? So why does its velocity change? The direction of the ball does not change. Well, if the boy hits it, it's going from one way to the other, so the direction will change, so it's not that. There is a resultant force on the ball, could be that. The mass of the ball increases. Well, just because you hit it, it doesn't make the ball heavier, so it's not that. And the speed of the ball is constant. Well, if just because you hit the ball, you might hit it with more force, so you wouldn't say the speed of the ball is constant. So it would be number 2, there is a resultant force on the ball. Remember, the resultant force is the overall force acting on the ball. So if you hit it with enough force, it would cause a change in movement, and therefore its velocity would change. The ball has an average speed of 11 meters per second. The ball takes 0.25 seconds to travel the same distance as the length of the table. Calculate the length of the table. Use the equation, distance travelled is speed times time. There's only 2 marks again, and they've given you it as distance travelled, so you don't need to rearrange the equation. So again, a nice simple times question. Your speed is 11, your time is 0.25 seconds. There's nothing funny about these units, so you would just times it together, and that gives you 2.75 meters. Okay, so question 3.3 then. A table tennis ball should only be used if it bounces to at least 75% of the height it was dropped from. A manufacturer tested the table tennis ball, and it shows the results. The height it was dropped from in centimetres, okay, and you've got the height of the bounce of the ball in centimetres there. So it started off at 30 and it bounced to 25.1. Determine whether the ball can be used. Okay, so what we've got to know is whether it bounces more than 75% of the height. So this is a percentage question. We want to know what percentage 25.1 is out of 30. So when you do a percentage, it's always the smallest one divided by the biggest one. So 25.1 over your starting height of 30, times it by 100, and that will give you 84%. Now we can see then that 84% is higher than the 75% that it has to be as a minimum, so therefore we can say yes, the ball can be used. Okay. Question 3.4 then. Figure 5 shows two table tennis balls. The balls are different sizes but have the same mass. Both balls were dropped onto the table from the same height. After they were dropped, the resultant force on the smaller ball was greater than the resultant force of the larger ball. Explain why. So the overall force on the smaller ball means it was going ever so slightly faster than the one of the larger ball. Why might that be? Well, the resultant force is the overall force. Now, the gravity would be consistent on the balls. So what other force, so if gravity is consistent, what other force is therefore different? Well, it would be the air resistance. So the air resistance is different. Okay, the smaller ball has less air resistance, and because it has less air resistance, the overall force is therefore bigger. Question 4 then. The thinking distance of a car depends on the reaction time of the driver. Figure 6 shows how the thinking distance varies with the reaction time for a car travelling at 30 meters per second. The reaction time of the driver can double if the driver is distracted. Explain the effect doubling the reaction time has on the thinking distance. Use data from figure 6. Well, what is happening then? Let's look at our numbers. If we start off at 200 for reaction time, we can see that it goes to a thinking distance of 6 meters. If I go to 400, I can see going along on the graph, it's equaling 12 meters. And if I double it again to 800, well, it's gone all the way to 24 meters. So I can see what's happening. If I double my reaction time, I am then doubling my thinking distance. Okay, so explain the effect doubling the reaction time has on the thinking distance. If you double reaction time, you double thinking distance. Okay, and then for the second mark, so that would get you 1 mark. For the second mark, you would have to quote data. So I might say from my examples here, e.g. at 200 milliseconds, it gives you 6 meters, and at 400 milliseconds, it gave me 12 meters. So just quote some data from your graph there to support what you said. Question 4.2 then. Give the reason why there are no values for thinking distance for reaction time less than 200 milliseconds. So why can't we calculate a thinking distance less than 200 milliseconds? Well, it just comes down to basic biology then. People generally can't react faster than 200 milliseconds, therefore we can't work out any thinking distances. So it's just people cannot react faster than 200 milliseconds. A driver measured her reaction time using an online test, and she did it 5 times, so it shows you her results below. How does the data in Table 2 show that it was important that the driver did the test 5 times? Well, we can see that why is it important she does it? It goes from 258 to 265, then goes much higher at 302, then it comes down again, okay, then up again. So why is it important that the driver did it multiple times? It's because there's a lot of variation. Or you could say results not consistent. Or you could even say a lot of error. Anything like that, that would get you the marks. Question 4.4. calculate the mean reaction time of the driver. So what you'd need to do then, is just calculating the mean, you would add them all up, 258 plus 265 plus 302 plus 248 plus 327, add them all up, divide by how many there are, which is 5, and then that would give you a mean reaction time of 280. Okay, so question 4.5 then. The driver is driving her car at 30 metres per second. Determine the thinking distance. Use figure 6 and your answer from question 4.4. So we worked out at 4.4, it was 280 milliseconds is her reaction time. We've got to use figure 6 to then work out her thinking distance. So we can go back to the graph, okay, and we can see, if I get rid of my old annotations, that 280, where if I go to 200 and 400, 300 will be bang in the middle, 280, each little square is going to be worth 20, so 280 would be that one going along, so I can see it's roughly about 8 meters. Okay, it might be a little bit halfway in between. You would use a ruler, and in fact it gives you a value or a range of any answer between 7.9 meters to 8.9 meters, assuming that your answer to question 4.4 was right. If you got this one wrong, you would get error carried forward, and then you would just match it up whatever result you got from question 4.4. Okay, so question 4.6 then. So, the driver applies the brakes and the car comes to a stop. The force exerted by the brakes affects the braking distance. Give 2 other factors that affect the braking distance. Well, the braking distance of a vehicle is everything to do with the actual vehicle itself, but also the road conditions. So you can have anything from the quality of the road surface. Okay, you could have condition of the tyres. You could have weather conditions, such as rain or ice. Or you could then go on about the actual car itself, so the speed of the car and or the mass of the car. So basically it's everything to do with the car and the road, nothing to do with the driver itself. So the driver is the thinking distance, the braking distance is the car. Write down the equation that links distance, force and work done. So this is the equation you need to know. Work done equals force times by distance. It then says when the driver applies the brakes, there is a constant resultant force of 6 kilonewtons on the car. The car travels a distance of 75 meters before stopping. Calculate the work done in stopping the car. So we've been given some numbers and we'll be using the equation as we wrote it above. Work done equals force times by distance. So my work done is what I'm calculating. My force is 6 kilonewtons, where a kilo means 1,000. So a bit like kilograms or kilometers, you would times that number by 1,000. So 6 times 1,000 is 6,000, times by the distance travelled, which was 75 meters. So I would then do 6,000 times by 75, which gives me 450,000 joules. Okay, and that would be the amount of work done to stop the car. Work done, if you just remember, is energy transferred. Question 5 then. The sun emits all types of electromagnetic waves, and it shows the electromagnetic spectrum there. So you've got gamma, X-ray, ultraviolet, visible, infrared, microwave, radio. Obviously, we, as humans, only detect the visible part of the spectrum and the visible rays, but we've got all of these other frequencies that are going around us and through us that we can't detect. It says, complete the sentences and choose the words from the box. So in a vacuum, all electromagnetic waves travel, and the answer is at the same speed, but speed isn't on here, so we have to use the closest word, which would be velocity. So even though radio waves have a really long wavelength and gamma rays have a really short wavelength, all electromagnetic waves, the transverse family, they all travel at the same speed in a vacuum. So therefore, it then says gamma ray waves have the greatest blank. Okay, well, we've just said gamma rays are really close together. They have the shortest wavelength. And as they have the shortest wavelength, they have the highest frequency. So the answer would be frequency. And therefore, radio waves are the opposite of gamma rays. They've got a really long wavelength. So that would be your answer there. Radio waves have the greatest wavelength in the electromagnetic spectrum. Explain why it is important that the Earth's atmosphere absorbs gamma rays emitted by the sun. Well, the atmosphere plays an important point, and it stops us being absorbing too much gamma rays. Gamma rays are really high frequency, high energy waves, and they can be damaging to humans. Okay, so the atmosphere then fortunately absorbs a lot of them for us, so we are not exposed to them. So we could summarise the answer into 2 points by saying, so people or humans are not exposed to too much gamma rays. Okay, so it does not damage human tissue, which could potentially cause it to mutate and cause cancer. Okay, some microwaves are not absorbed by the Earth's atmosphere. Why is this useful? Well, microwaves, if we think back to their uses and how we use them, they're used in communication. For example, satellite communication, but even mobile phones. Okay, so that is how our signals go up into the atmosphere, bounce off a satellite, come back down to the receiver, and they would use microwave radiation. So microwaves can pass through the atmosphere. Some ultraviolet UV radiation from the sun passes through the atmosphere and reaches the surface of the Earth. The amount of radiation that reaches the surface of the Earth can be measured on a scale called the UV index. Figure 8 shows the average midday UV index in the UK for 1 year. Question 5.4. Why is exposure to UV radiation harmful to humans? Well, this is the danger of ultraviolet. What can ultraviolet waves cause? It's not strong enough to get through our bodies and cause internal cancer, but it can cause skin cancer. So think of UV sunbeds that some people go on. Although it might give you a tan, it can mutate the cells in your skin and can give you skin cancer. You could also get away with just saying it would cause a lot of sunburn. Question 5.5. Compare the risk of UV radiation at different times of the year in the UK using figure from figure 8, and you've got 2 marks. Okay, so it's saying effectively when is it the most dangerous, when is it the least, and you've got to support it with data. So just reading off the graph, we can see July has the highest UV index at 9 UV index, whereas the lowest would be December at about 0.75, okay, UV index. So therefore, we could summarise it by saying the risk of UV is greatest in July, or the summer. And then you would need 2 readings from the graph to support your answer. E.g., as we just said, July is at 9, and then December was obviously much lower. So that's how you could get 2 marks there. If it tells you to use data, pull some numbers off your graph or table. Then, question 6 then. Figure 9 shows a runner using a smartwatch and a mobile phone to monitor her run. Figure 10 is a velocity time graph for part of the runner's warm-up. Okay, so this is her warm-up, and you've got time in seconds, and you've got her velocity at the side. So before I even start thinking about the question, I would annotate this graph with what I know. So I can see as velocity is going up, the first section shows me an area of acceleration. Then I would have constant speed. Then it goes up again, so it's accelerating. And then you'd have another faster area of constant speed. And then as it's going down, it would be decelerating, going down. Question 6.1. Determine the total time for which the velocity of the runner was increasing. So we're just looking when or how much time were they accelerating for. So I can see starting off, my first section goes up to 4 seconds. So my first section is equal to 4. And then I can see that my next section starts at 7 seconds and it finishes at 10 seconds. So I've got a gap of 4 and I've got a gap of 3. So therefore, if I add these numbers together, that would give me a total amount of time of 7 seconds. So my runner is accelerating her pace for 7 seconds across that graph. Determine the deceleration of the runner. Now the equation for deceleration, we can use the equation for acceleration, which is the change in the velocity divided by the time taken. Okay, so if we go back to the graph, we can see her deceleration starts at 2 and ends at 0. So therefore, her change in her velocity is just simply 2. 2 minus 0 is 2. Then the time taken to do that, well, she's starting at 14 and she's finishing at 24. Just reading the numbers from the x-axis. So 14 minus 24 gives you a gap of 10. So I would just do 2 divided by 10, which would give me 0.2 meters per second squared. They've given you the units, so it would be 0.2. You could say negative 0.2 meters per second squared as it's decelerating, but you wouldn't lose a mark if you didn't. The smartwatch and mobile phone are connected to each other by a system called Bluetooth. Bluetooth is wireless and uses electromagnetic waves for communication. Suggest why the phone and the watch being connected by a wireless system is an advantage when running. Okay, so it's just a suggest question. So it's a common sense 1 mark suggest question. Why is having wireless Bluetooth to the headphones and the phone an advantage when running? Well, what's the issue with running and wires is that they can get tangled. Okay, so you could say wires do not get tangled or disconnected. Write down the equation that links frequency, wave speed and wavelength. Well, the one you need to know is wave speed equals frequency times by wavelength. So if I then look at the next question, the electromagnetic waves have a frequency of 2,400,000,000 hertz, and the speed of the electromagnetic wave is 300 million meters per second. Calculate the wavelength. Well, if I'm doing wave speed equals frequency times by wavelength, I want to make wavelength the subject of the equation. So in order to get wavelength by itself, I would do the inverse, the opposite of this times by frequency. So I would divide by frequency. So therefore, wave speed divided by frequency equals wavelength. I could then substitute in my values. So my wave speed is 300 million, making sure your zeros are right, divided by your frequency, okay? Okay, and if you plug that correctly into your calculator, that would give you a wavelength of 0.125, and it's given you the units of meters. If you rounded it up to 0.13, that is absolutely fine. Question 6.6, Table 3 shows information about 4 types of Bluetooth. Most mobile phones use Bluetooth Type 2 to communicate with other devices. Give 2 reasons why. So let's have a look at their power and the range in meters. Well, we can see Bluetooth Type 1 uses an awful lot of power, okay, and it gives a range of 100 meters. Bluetooth Type 2 is much less power, but has a range of 10 meters. Type 3 and Type 4 are less power, but their range in meters is much smaller. Okay, so you could say 2 reasons why. Well, the range of 10 meters is enough for a runner. Okay, and then you could say the power is very low compared to Type 1. Okay. So therefore, as the power is much lower, the battery will not be drained. Okay, so question 7 then. Figure 11 shows the equipment a teacher used to determine the speed of a water wave. This equipment includes a ripple tank that is filled with water, a wooden bar that creates ripples on the surface of the water, and a light source which causes a shadow of ripples to be shown on the screen. So you've got here the light source, the tank, the water ripples, and then you've got the screen being shown below. Describe how the equipment in figure 11 could be used to measure the wavelength, frequency, and speed of a water wave. So it's saying, how can you use this to determine these 3 things? Wavelength, frequency, and speed. So let's just start with one of them at a time. The frequency is how many waves pass a point each second. So how many waves pass one point each second. So if it is per second, the easiest way to do is identify this 1 point and then count how many waves might pass it in 10 seconds, okay, and then divide it by 10. Now, this is sometimes quite hard to do with the naked eye, so you could get a video camera, record it going across for 10 seconds and count how many and then divide it. So what I would do is set up a video camera. You would then record it for 10 seconds. You can then go in slow motion if you need, but you count the number of waves that pass 1 point in the 10 seconds. And then to calculate the frequency, you would divide that number by 10. Okay, so you can effectively say your frequency is 1 divided by the time. Okay, then, so that's how we could get our frequency. We could then look at our wavelength. Now the wavelength is the distance from one wave peak to another. Doesn't have to be from peak to peak, it could be from trough to trough, or it could be from midpoint of a wave to midpoint, but as long as it's consistent. Now the wavelength we measure in meters. So again, what we can do potentially is on our screen, if it's difficult to see with the naked eye as it's going along, is take a photo. So take a photo of the screen. And then you can measure the distance with a ruler. With a ruler between two peaks, or between two of the lines, and that would give you the wavelength. So you can use a video camera to get your frequency, and you can use just a normal camera to get your wavelength. And then to calculate the wave speed, well, if you know wavelength and frequency, what you can do is times wavelength times by frequency, and that would give you your wave speed. But if you also wanted to demonstrate it practically using this equipment, well, you can use the equation speed is distance over time. You find the distance of your tank, okay, then you find and you record the time it takes for one wave. So record the time it takes one wave to travel along it, and then you can just use your standard speed is distance divided by time equation, and that gives you the wave speed. Now you've got to describe each of those methods to get you into the level 3 category, which will give you 5 or 6 marks. The teacher then put a plastic duck in the ripple tank as shown in figure 12. The plastic duck moved up and down as the waves passed in the water. How does the movement of the plastic duck in figure 12 demonstrate that water waves are transverse? So this is your difference between a transverse wave and a longitudinal wave. We should remember in a transverse wave, what happens, the particles are vibrating up and down. Okay, so if the wave is travelling from left to right, the particles are vibrating up and down. So we say the particles vibrate perpendicular to the direction of the wave. Okay, the particles or the duck move perpendicular because it's the particles that are moving the duck. Now, you can't say, because it is at the end of the paper, so it's quite a medium demand question, you can't just get away with saying the duck is moving up and down. That's not detailed enough. You need to remember the key language, that the particles vibrate perpendicular to the direction of travel. Remember, if it was a longitudinal wave, they vibrate parallel to the direction of travel. Last question on this paper then. The teacher measured the maximum height and the minimum height of the plastic duck above the screen as the wave passed. The teacher repeated his measurements, and it shows the teacher's measurements below in the table. So you've got the maximum height of the duck and you've got the minimum height of the duck. It says calculate the mean amplitude of the water wave. Okay, so remember the amplitude of a wave, if I draw out a wave here, is half the height of the wave. The amplitude is the distance from your midpoint to the peak of the wave. Okay, we've been given the maximum height average, and we've been given the minimum height average, and we want to find this midpoint here. Okay, so the way of doing it, well, you've been given 3 values for each, so you can start off, if you've been ever get 3 values, calculate the mean. So the mean of the maximum height is 511, add them up, divide by 3, gives you 511, add the 3 bottom ones up, add them up, divide by 3, gives you 500. So our maximum height on average is 511 millimeters. Our minimum height is 500 millimeters. So the amplitude is going to be the midpoint of these two parts. So obviously for difference, 511 minus 500 gives you 11 millimeters. That is our difference, where we want to divide it by 2 because you want the midpoint, which is 5.5 millimeters. So that gives us 5.5 millimeters. Therefore, our amplitude is just simply 5.5 millimeters, okay? And therefore that would be our final answer, and that would give us the 3 marks. So that's the end of this paper then. Again, there's a copy of a blank paper and mark scheme in the description, along with revision videos for the content if you need to go back and revise it. Hope it's been useful. Thank you very much.